that goes away.
Well, all right. So today I'm going to be talking about a very specific class of models, which is called state space model, and that have kind of eluded the attention of high-dimensional specialists for the past 25 years or so. It's mostly joint work with Axel Finken, who's at Loughborough University, but he's going to move in Newcastle soonish. He did also some work on that with Alex Thierry, who's in Singapore, and I did some of the work with Simo Saka, so my former supervisor in Aalto University in Finland. All right, so to kind of like set the context, state space models are usually traditionally used to model dynamic processes that are observed with some noise. So a good example is epidemics, whereby you have a population of infected that evolves over time, and you just kind of observe a subpopulation of it sometimes, right? And you're trying to do inference on the latent population, but also on the characteristics of the epidemic itself, right? And that would be parameters of the state space model. Climate, weather, so anything where you have evolving physical phenomena that are observed here with satellites, and it's pixelized with cloud coverage, and you're trying to kind of like remove the cloud coverage, which is, you know, a noise or more so like a mask of your data. An interesting one, fairly recent, is federated inference. So if you look a bit into the work of Murray Pollock, Hong Sheng Dai, Gareth Roberts, and Corenflos, they can they managed to phrase the problem of federated Bayesian inference as a problem of inference in a state space model, whereby you start with independent populations and you end up in a system where everybody is eventually the same. And that's kind of how you want to phrase federated inference. Also, diffusion models, large language models, all of these are essentially processes that evolve over time, and you want to do inference in them, and they are by construction fairly high dimensional. All right. So conditional sampling in diffusion models is a form of state space model. All right. So if we want to do inference in them, what do we want to do? Well, we want to infer the state with good scaling in terms of the time, by which I don't mean computational time here, I mean the number of time steps, right? So the number of observations over time. And the dimension here, what I mean is the dimension of the observation, right? So if you have a very high dimensional problem, then you typically have a fairly hard problem. You want it to be easy to use, and you want it to be consistent. And by consistent, here I mean in the sense of MCMC, by which if you just take samples or add compute over time, you get closer and closer to your problem, or to your solution. So there are methods to do that. They are expensive, usually either scale well in the time dimension or in the observation dimension, and they're fairly hard to tune. I mean, if you want to kind of use them out of the box. So here, what I want to talk about is an automated way to kind of get something that scales well in the number of time steps, scales well in the number of dimensions, and is fairly easy to tune, or at least robust to tuning in some sense. All right, so the formalism is one of the underlying dynamics, so x1, x2, etc., up to xt, which emit observations. All right, so it's typically related. They're typically related in terms of a function that takes the previous state and some noise. So Markovian state and observations that take the state, some noise, and I mean emit some random variable. All right. We'll see a generalization of that in a bit. And the smoothing problem, so the actual inference problem, is to get the joint distribution of all the latent states given all the observations. All right, and you can add a parameter if you want to that. There are other problems. Filtering is essentially like that, but for each time step and only the final state, not the previous ones. But what we actually care about here is the smoothing one, which is essentially the big problem. And the dimensions, t, the time, dx, the state, and dy, the observations. In practice, what I'm going to be doing here is you can think of dx equals dy mentally, a bit like when you would do scaling for MCMC methods. And the time is just the number of observations. All right? Okay. So again, we want time scaling, dimensional scaling, and consistency. Why do we want that? Well, it's because it allows us to create computation for precision, right? In a way that is not exponential in the amount of computation. And it also allows us to do parameter inference. Because like the state posterior is usually used to do parameter posterior via clip sampling, yada, yada, right? Right. So if we look at past work, it's not exhaustive at all, all right? In fact, I'm happy that Alex Beskos is not here because I probably should have talked about one of his papers in there. You typically can take dimensional, so you typically can get dimensional scalability, so in dy, time scalability, so in t, something that works well in t, or consistency, but not the three of them, all right? So if you look at dimension and time, so something that scales well in dimension and time, it's typically going to be approximate. You have ensemble Kalman, which maybe some of you have heard, that's used a lot in weather prediction. You're going to have essentially local particle filters, so things where you look at your space and you kind of like solve exact problems in subspaces and then try to stitch them, and factorial locality, which is that, but with a more algebraic type of local perspective than a geographical, in a sense. But they kind of all think in terms of locality. You can get dimension and consistency, and for that, you just pick your favorite MCMC method, and you just slap it at the problem, and you hope for the best, right? And you can get consistency and time scalability, and that will typically be methods inherited from particle filtering. All right, so the one that we are going to be talking about today most is particle GIFs. All right. And so the question is, how do you get the three of them? So what we're going to be doing here is that we're going to be combining the particle filtering approach and the standard MCMC approach in a way that gives us both scalability in the dimension and in time. All right. So why do we want to do that? It's kind of known that MCMC is building dimension. So here, if I just look at, so this is a state-based model, just Gaussian, I think it's 10 time steps, 25, can't remember. And I'm just increasing the dimension of the observation. And so what you can see is fixed number of time steps increasing dimension. All right. What you can see is conditional efficiency, which is the particle filter-based method, collapses very fast as the dimension increases. So this is the expected quadrant distance, which is a good measure in some sense of the efficiency of the function. The higher the better. On the other end, Mala, the legend is small, but so the blue is a particle filtering base, so it's sequential Monte Carlo, and this one here, reddish, is Mala. It scales much better, so it kind of like goes down to zero, but slower, all right? And that's kind of what you want with in terms of the dimension. On the other end, so this is for a fixed dimension and increasing number of time steps. You have Mala that decreases exponentially, right, to zero. Whereas the CSM scale, you can see like it's very stable. It actually doesn't move at all. So we kind of want to get those two behaviors, but combined, right? And that's eventually what we're going to get. And what I'm going to be talking about today, and I'm going to kind of like show how we do that. Like I'm going to discuss the tricks that relate to making that happen. All right. Great. If people are wondering why there's a gap here at the beginning, right there, so the green is because I only implemented it for t greater than 3, because otherwise it's painful. Okay. Any questions so far? No? Great. So how are we going to talk about that? So I'm going to make a small sidestep in the world of MCMC, specifically the world of auxiliary variable-based MCMC, right? To kind of explain the structure of the samplers we're going to consider. And then I'm going to give a semi-introduction, semi-presentation of what SMC is. And I'm going to present it as a form of repeated and sample MCMC, right? Trying mostly to stay onto the intuition more than the actual formalism. Once that's done, I'm going to combine the two, and then we'll see what happens. Yeah? So this is actually a bit of a mind stretch for me, or at least the first time I saw it. MCMC is essentially Gibbs, all right? But I'm going to show that it's exactly Gibbs. So when I say MCMC, I mean Metropolis Hastings, all right? So with acceptance rejection. So what is standard Metropolis Hastings or Rosenbluth? So if you have a sample X that you assume coming from your stationary distribution of interest pi, you propose a sample Y, right? Then you compare the two via an acceptance function, and then you either accept or reject Y as your new sample with probability, the minimum of 1 and the ratio you see here. And this is Metropolis Hastings, right? I think people at UCL probably know that, but there is also Barker acceptance, right? That Sam has been pushing for a bit, which corresponds to doing the same thing, but with a different type of balancing function. And it also works. It's just a bit less efficient. All right. Okay. So let's look at the structure here. We have X and Y. So X, then Y. But it really doesn't make sense to have an ordering. In practice, I can kind of like muddy the water a bit and say I just have X node, X1, and the variable K, which corresponds to which one I'm considering to be stationary. All right. So here, you just kind of think a step back. You say if K equals 0, then X node would be X, and X1 would be Y, right? And vice versa. But I've kind of like made that a bit more symmetric. Okay. What I'm saying is Metropolis Hastings with that specific Barker acceptance is just a Gibbs sampler for this augmented distribution. All right. So we start from here. Given K X naught X1, I sample X1 minus K according to my proposal. And then I look at the distribution of K given X0 and X1. And it's a categorical distribution with two weights. W0 equals that, and W1 equals 1 minus that. Okay. The first time I saw that, I was a bit shocked. I mean, not shocked, but it was a small eureka moment. So you can actually just say MCMC is just Gibbs, and it's really nothing. Okay, so we compare, right? We sample, we come from X, we sample Y, and we accept or reject with a weight that corresponds to the ratio of the densities. We sample from the proposal, we look at the weights, and we sample K, right? And then XK is your sample from your target. Bit weird, right? Okay, so why do we care about that? Well, we care because this is only for one proposal, but it allows you to do it for many. So if I now say my augmented distribution is XK, stationary, and then a bunch of other samples, right? X0 to K, but we remove the small K one. Okay, I can just write down this K. And for K equals 1, right? Capital K equals 1, I just recover what I had before. Okay, makes sense? Then what I'm saying is, this is correct. I start from X, I sample a bunch of particles, I compute weights, and then I select the next state with the corresponding probability. I've just generalized the MCMC to many particles. Okay, I mean I haven't, but those people have. Right? All right. Okay, so the main issue with that is that it's expensive, right? So you have to kind of look at the joint density of a bunch of particles given one. So that's something which is going to cost you for each element in the denominator k evaluations mentally, right? So you end up with something which is quadratic in the number of particles just to compute the acceptance step. But you can get rid of that by using an auxiliary variable, and that's the first time we get one. So you start from x, you sample a centering variable, and then you radiate around it. All right? And that breaks that joint distribution into two steps. The first one, I sample u. The second, I sample all the xj's conditionally to on u. And if you integrate u out, then you get the previous framework. All right? And so I can do sampling from my stationary distribution by using this framework. And a few examples would be, for instance, the random walk, where my auxiliary variable consists in doing half a step of the random walk. And then I just sample from you another half step, all right? And then I accept or reject that. So you can just say random walk metropolis is essentially something you do in two steps. You can do it with Langevin, where you say, okay, my first step is going to be a gradient one. And then I'm going to do a small side step according to random walk, all right? And that would be a Langevin proposal. Make sense? You can do preconditioned. Well, okay, and that looks like that. Sorry, I forgot the graph was coming. So the random walk, you sample an auxiliary variable, which is going to be essentially creating an exchangeable set of particles around the auxiliary variable. Whereas the Langevin, because the u variable is a bit small, you break the exchangeability, but it doesn't really matter because everything works. All right? You can create preconditioned version of that. So if you have a Gaussian prior, then you can just say, okay, I'm going to take a half step of my Langevin, and then I'm going to do a condition, like a preconditioned random walk, right? I've not written the formula, but it's just Gaussian algebra. But you can also do independent metropolis with that, right? I just put an improper prior on the U distribution, right? And then I just take a proposal that's completely independent of U. No problem. Okay. So to summarize, start with X as the station, X as stationarity, sample U from your auxiliary distribution. For each other particle you want to consider, you sample from the proposal X given U. Then you compute your weight and you select the particle according to a categorical distribution. Okay. So in practice, you can also do this step a bit more efficiently by a metropolis Hastings, something that looks more like a metropolis Hastings and not a Barker, but it muddies the water, so we'll just think about Barker. Okay. Okay. Questions so far? Great. Okay, so we're done with the auxiliary MCMC. And now we're going to talk about SMC as repeated ensemble MCMC. So essentially, we want to repeat this procedure over and over again for the models that we consider, so the state space models. And to kind of like fix our mind, like to fix our ideas, let's consider a model that is fully factorizable. So something where all the quantities of interest are fully independent. All right. In that case, I can be very myopic, a bit silly, and I can do MCMC directly into that. All right. So if I think of independent metropolis, I can say, okay, well, this is just the posterior distribution for a triad, which is the product of the P of XT. All right. So I'm going to sample from my trial, and I'm just going to accept or reject. All right. If you do that, then the total acceptance rate is going to collapse exponentially fast as the number of time steps here increases. All right. And it's just a matter of doing independent metropolis things in a space of increasing dimension. It works worse and worse as the dimension increases. All right. And you're going to tell me, well, Adrien, like you're a bit stupid here, right? So why are you doing that? Instead, just do it time step by time step, right? The problems are independent, sample them independently. What are you doing? And you'd be right. If I do that, then the average acceptance rate is going to stay constant. All right. Yeah, I mean, because the things don't depend on T, right? But I'm going to get something that's going to be consistent in time, and I've not artificially made my problem harder. Okay? So we want to emulate that kind of system for models that are not directly products, but have that Markovian structure, which is, you know, like the next best thing after a product. Okay? By the way, the same thing happens if you just take Barker, right? It's not a question of the acceptance rate, of the acceptance probability. Okay. And so if we look at our target distribution of interest, it's pretty close to being that, right? You have a bunch of distribution xt given xt minus 1, and then you have a bunch of potentials, right? And it's almost a product, except that you get communication via one term each time. And so we want to kind of do something that looks similar. And thankfully, that thing exists and is in a paper by Adrien, Doucet, and from 2010. I think he left academia, so I can't remember. And it essentially consists saying that if you have a reference path, X star, so the current state of your Markov chain, which corresponds to the smoothing criteria, you are at a given time step t, you're going to sample a bunch of xt, sorry, you are the sample at a time step t, you have a bunch of samples, xtn, you're going to look at their weights corresponding to the likelihood function of your observation, compute the corresponding weights, kill or keep them. That's a selection function. It's actually the same one as the Barker we had, which corresponds to these lines that we're drawing. So here I'm saying all of my particles come from that one. So ATN is going to essentially be one of those two. I don't know if it was only red on that one or just the red side. Whereas those are too far in the tail, they are not going to be selected. All right. And you do that, you do it again and again and again. All right. Until you reach the final stage. And that creates a grid of potential trajectories. And then you're going to select one out of them. And that's the green thing. All right. So I'm not going to go into details about exactly how we do that green selection, or the fact that, in fact, if you have seen here, we have n+1 and I'm starting n at 1. Those are essentially just tricks to make the detailed balance condition work in the resulting MCMC. But fundamentally, what you're doing is you're creating a grid of potential trajectory and then picking one out of them.
So what is the role of the reference part? It does there anywhere else. There's X star, and then I didn't see X star anywhere.
So X star appears in the weights.
Well,
so the weights are indexed from 0 to n.
Yeah.
Right. But I'm only simulating particles from 1 to n. So I'm saying that the particles at time t. So here it's a good. So the particles at time t might come from that red one. All right. So if you look,
so n equals 0 is X star.
so yes,
Yes.
yes. Did I know?
But you went for x0 as
Yeah. Okay. Sorry. Yeah. So x0 is your current the current state of your Markov chain, right? And then it appears in the weights, which means that well, you see that I'm only sampling 80n from 1 to n, so all the 80 are 0 by construction. And then when I'm sampling, I might actually use the reference. So I might use the current state of my Markov chain, for example, my next proposal. Okay. All right. And so that creates a Markov chain for your Markov chain. So you have that the posterior of the state-based model. You have the red trajectory, which is distributed according to the smoothing posterior. And once you select your green one, it's also distributed according to the smoothing. And as you can see, it looks very, very much like an ensemble MCMC, right? But repeated over time. We've just spread a bunch of particles, selected a few, spread a bunch of particles, selected a few, and over and over, right? Okay. So based on that, what we're going to want to do is create variables in this, right? But let's quickly look at why we want to do that and what happens in the high dimensional setting. So it didn't. Sorry. So here I've written it for observation functions, y of xt. But by the way, it also works if you have potentials that depend on xt minus 1 and xt minus 2 and xt minus 3, xt minus 2, xt minus 1 and xt. It's just that it becomes a bit ugly, but you can compute it. And by the way, this is why people don't like SMC, right? All right. So that being said, when the dimension increases, fundamentally, the observations become more and more informative, right? The dimension of your observation increases, means the total amount of information you get is larger and larger. So you get more and more informativeness, which means that the weights essentially concentrate around the state. It's your Laplace approximation, right? You can think of it like that. And so it means that when I look at my particles and I compare them with my likelihood function, they're going to have very, very small weight, which means that they are never going to be appearing in this ancestor, right? That essentially means I remove them from the pool of potential future states. And when I do that, the green, so like the next state, essentially is going to have to end up collapsing with the previous one. I stop. All right. And that's because my proposals are too far away from the potential observation plan. I squeeze, all right, and I collapse. Make sense? So the reason for that is because if you look up close, this is an independent proposal. All right? It does not depend really on the previous state of the smoothing distribution, on the previous state of your Markov chain targeting the smoothing distribution. Back here, I just like I xt minus 1, right? We are back in the previous product of distribution, and we understand why independent metropolis does poorly. Okay? Okay. And so we'll want to use this representation of ensemble MCMC with this. Okay? And once we do that, instead of getting a collapse that has the particles not move, but the likelihood of the observations increase, that has the likelihood of the observations become more and more informative, but the proposal not adapt to that, we'll get something where the two kind of bring together so that you're able to map the space in a way that is coherent with the amount of information you have. You can think of a step size. All right. Excellent. So how do we actually do that? Questions so far? No question? Okay. All right. So here to kind of like give a bit more intuition, which I'm trying to kind of like push down your throats. I'm going to compare the static case and what I call the dynamic case. So the standard Bayesian posterior and the state space model posterior, which is in a sense a generalization, right? And I'm going to compare the two things. So when we do independent proposals in metropolis things, we say, all right, auxiliary variable is just a constant model. Auxiliary likelihood is a constant model. And I'm just sampling from a proposal queue, which is just my prior, or anything else. But in that instance, it's the prior. In the state space model case, it corresponds to augmenting the distribution of the state of the trajectory with an auxiliary trajectory, which does nothing. All right. And then I'm going to use proposals times over time, which are just given by the prior dynamics. And those two things are essentially mirrors of each other. Okay. Now, if I want to use random walk, I can phrase the random walk metropolis algorithm for static model as an auxiliary variable model, where I take a half step in an auxiliary space, and then I take another half space, and then I take another half space in the state. Another half step in the state space. Right, too many steps. Okay, and so the question is, if I want to do that in the state space model case, well, I can augment my target distribution with a product of small half steps. And then the question is, how do I create a proposal? Okay, so what do I actually sample my X with? Well, we're going to try and emulate the same thing. So we go from our state space model, we augment it with a bunch of local random walk half steps, right? And then we look at what we have. Okay, so what we have is something that has not changed in terms of the proposals, and then a bunch of observations, which are real ones, and all fake ones, right? Here, every time I'm assuming I've sampled DUs, and now I'm trying to sample X given it, right? But you can sample DUs trivially. So I'm doing a Gibbs step, sample DU, and then I'm trying to sample X given. So yeah, so if I look at my conditional model given U, I have a bunch of proposals, dynamics, right? So my trial, and then I've got observation. And I'm looking at it, and I'm like, what am I doing, right? It looks really bad because here, if I want to take a small step, delta, I'm essentially making my observation UT more and more informative, which means I'm making my problem worse and worse. It's as if I'm increasing the dimension of the problem. All right? I'm making spiky observations for very small delta because they have very small variance, which means I'm going to have like tension here. I won't be able to compute that thing. You know, like it's essentially saying that the prior, the proposals, are going to be essentially degenerate compared to the posterior. Okay. But I can use a trick, which is that I can just change the order of those, right? And it doesn't change anything to my proportionality. All right, I go from having the auxiliary variables as observations to the auxiliary variables as proposals. And it relies on a very complicated property of the Gaussian, which I've written here, right? So yeah, very, very, very complex stuff we are doing here. Okay. And so when you do that, you fundamentally go from particles that don't depend, so proposals that don't depend on the informativeness of your observations, to proposals that shrink as you shrink the step size. And in fact, you get the same scaling as standard random walk metropolis, the one that was derived in a paper by Corenflos and Rosenthal, I think, probably Rosenthal, or maybe it was well. And as you scale the step size as 1 divided by the dimension of the problem, your sampler starts working. All right. In short, it works. Okay. Yes.
So fundamentally, what you've given us here is a way of scaling the step size of the increments. But with the previous slides, you provided some kind of theoretical justification for doing that kind of thing.
Yes. It's so you have to look at it as a form of metropolis within Gibbs for an auxiliary model.
Yeah. But you could just simply think of, oh, why don't I let the steps depend on something, and then the algorithm still perfectly work without this kind of.
You get invariance, no problem. Yeah.
Yeah.
So invariance is automatic just because you're doing a metropolis within Gibbs.
Yeah.
Right. And both steps essentially keep the distribution invariant. But if you want a scaling result in terms of expected quadrant distance, so you want the expected quadrant distance to stabilize the dimension increases, to get a delta that looks like that.
Yeah.
Okay. Yeah. But yeah, otherwise you pick delta as you want, and it's even, I mean, it is going to be geometrically ergodic. It's just going to be very, very bad.
Yeah.
Right.
Unless you prove some kind of scaling result and derive the fact that delta needs to be like 1 over T1.
Yeah.
Something like this.
But in practice, you just calibrate it, right?
Yeah.
You just calibrate it. And it's really easy to calibrate because the delta T is independent of time steps, right? So all this kind of like local acceptance, which corresponds to all the particles like not getting rejected at the given time step, only depends on what you put at delta T here.
Yeah.
First order, right? So it's very, very easy to calibrate.
You have a different delta T for each time step.
Yes.
And
because it depends, like you might not have the same dimension of observations for each time step, the same informativeness, but you calibrate them all together. And the way you do that is you just look at the variance of the weights here, and you keep that at something constant.
so how do you actually sample X naught T given U naught T? You just give
Gaussian.
So
This one.
the whole trajectory.
So you do that you do that specific, like specialized repeated level MCMC, but where you replace the sampling of X given X minus 1 by that. And then you just look at the weights that you obtain. If you do this,
But could you do it the other way around? Could you sample from the dynamics, put that bit in the weight?
yeah, but then you get dimensionality collapse.
Right.
So that's, you would get the same thing, right? In fact, it would be worse. Yeah. Worse than that. Okay. All right. So we've done random walk. I said that auxiliary and CMT work with Nala. Maybe we should do both. Right, so random walk proposal, you augment with a Gaussian UX half step size, and you do the same thing for the state space model. Langevin proposal, you augment with a half Langevin step, right? And then you propose according to half random walk. Okay. And so the first question you have here is, yeah, sure, but like what gradient should I use here? Because I'm looking at the variable at time t, all right? Moving it according to xt, which is, I mean, it's the mean you can give that function, right? What gradient should I use? It's not clear. Okay, it's not clear to me. And so what we have is essentially two natural choices. And to introduce the two natural choices, I'm going to introduce what we call the filtering distribution. So it's the smoothing one, but up to a small time step t. So it's kind of like the partial smoothing, if I may. And in that case, what we can put in the gradient is either the filtering gradient, which corresponds to looking at the filtering distribution, right? Stopping the observation at time t, and then taking the gradient. And it corresponds to looking at the gradient of the dynamics at time t and the gradient of the observation, right? So that function only depends on xt minus 1 and xt. Even though it looks like I'm taking the gradient with respect to the full trajectory. Or I can take the smoothing gradient, and in that case, I need to take into account future interaction. Okay, so how does my state at time t impact my future dynamic? Make sense? Just a bit of you take the log, you take the gradient, and that pops out, right? So the difference is here I depend from I depend on xt minus 1 xt. Here I depend on xt minus 1 xt and the future. All right. So that's what makes it work better, but it's also what makes it a bit more complicated to handle. And so once I've done that, I essentially do the same trick as before. I look at my augmented distribution. All right. This is with the filtering gradient, and then I just inject a Gaussian, and I compensate for it. Okay, and this is also a very hard trick. It's 1 equals a divided by a. This, I mean, okay. So once you do that, you essentially end up with a fairly similar system where you can also collapse your particle proposal with the informativeness of the distribution, but you also get gradient information on top of it, so it typically works empirically better. All right. If you use the smoothing gradient, it's a bit more painful, right? So it's annoying to implement, but it can be done, and I have done it, so you can use it without having to care about it. But so you look at the weights that corresponded to the filtering problem that we had before. So you look at the filtering gradient augmented distribution and what we've been doing, and you call that GF, right? That weight that we had obtained. And then you just put it together with a form of compensation. And the compensation is to say, I'm actually trying to target something that depends on the smoothing, but in my proposal, I've used the filtering, so I need to divide by it. So it's again the same thing. 1 equals a divided by a, right? Okay, and when you do that, you get a big weight function in these weights that we have that now depend on xt minus 2, xt minus 1, and xt. So like a big thing. It's annoying to implement, but you can do it. All right? And same thing. You just need to kind of change the way you handle the weights, and everything just follows through. So now that we've done MATLAB or done what, right? A question is, yeah, sure, but like you have a proposal which conditionally on your UTs was essentially a product of Gaussians that were independent, right? Which means that you go from a problem that's fundamentally dynamic and you're approximating it by a mean field, right? And then doing metropolis testings with that mean field, auxiliary mean field. And that's not great. Why is it not great? Well, because if you have something which is low dimensional, CSMC, like the state of the art, really works. It really, really works, and it's really easy to implement. And if you have something which is very high dimensional, then what we've developed really, really works as well, right? So whenever you're in between, it's really not clear what you should do. Okay. And so how do you handle it? You combine both. You combine both. And the nice way to combine both, it's not the only way, is to use local contribution. All right, so you say, okay, let's assume that my dynamics were Gaussian, right, conditionally Gaussian, or if they're not, you just introduce the conditionally Gaussian and you correct for that in the weights by doing 1 equals the ratio of the same factors. And then all you need to know is to know how to sample from this Gaussian in XD and the Gaussian in XD. And you know how to do that. You just Gaussian algebra, right? In fact, in the case where you have something which, when you have something which has a linear Gaussian dynamics as a prior, then you know how to do something much better. You know how to sample xt given xt minus 1 and all the observations that happen in the future. All right, and so you're able to kind of marginalize out all the future observations in your proposal. That's pretty cool. And so we look at the random walk. We had this model, right? And originally, I had moved the Gaussian XTU here, and then I pushed my dynamics into the observations. So here in my observations, I had YT, YTXT, and I had also the trial dynamics, right? But if I use the one where I've integrated all the future auxiliary variables, right, then I have dynamics that take everybody into account, and then I'm only left with observation. So I have something which is gonna be fully adapted. All right. Damn. That's not cool. I'll give you access. All right. All right. We have access now. And you refresh. Nice. All right. And so what we can do now is we bridge in between by using local auxiliary conjugacy. Right. And so we end up with a simplified theorem which corresponds to a form of interpolation. And so instead of, come on. Come on. All right. All right. So instead of phrasing the theorem, I'm kind of going to explain what's going on with dynamics with a small video. So here is the efficiency of the sampler relative to this. I'm sorry about the quality. I didn't check the pixels. So the line in the middle at 1 is so we're looking at the efficiency of the free samplers. So in black is going to be the one that doesn't have step-sided, right? So the conditional FMC, which is the 2010 data. The blue line, which is going to start at the bottom here, is going to be the one where we take step-sided but not use prior information about the dynamics. And they are both going to be relative to the one where we have used the conjugacy of the two, right? So when you are above 1, you're better than the one where we use conjugacy. Where you are below, you're worse. And so as you can see, so you can think of this as being the dimension of the observation. So very low dimensional, very high dimensional. So this is the one where we've not taken into account the prior dynamics, and it starts really, really poorly compared to both TFMC, so the one where we use the prior only but no step size, and the one where we use both gradient information and the prior. Okay. Okay, so really, really bad. At some point, because we take small step size, small steps in our MCMC, the one with just global moves, so the independent metropolis tastings version, starts outperforming, right? Because it's able to take global moves and the dimension is not big enough yet to be penalized for that. That peaks at some point, right? And then you start paying the price of the dimension increasing. And after a while, as the dimension increases, the knowledge you have from the prior dynamics becomes irrelevant, and you start failing compared to the models where you have step sizes, right? Whereas the one where you use the information in your of your gradient starts overperforming and then reaches the one that interpolates. And so why is that one really tiny bit better than the one where we have prior information on dynamics? It's because the blue line was using smoothing gradient, whereas like the central line was using filtering gradient. Okay, and the next video would have been with the one where we take all the filter into account, but one, I don't have the time, and second, I don't have access. So, so now that this is said, the main conclusion is really that there is a love relationship. Yeah, right. You can really make them commingle and love each other and use both the particle filtering methods together with your standard gradient-based MCMC methods, right? And it works. There's still lots of work to be done. So the step sizes are easy to calibrate, but we might want to do that in a one-shot manner just because we have information due to the dynamics. We might want to use different samplers, so HMC, Barker proposals. We have a proof of the dimensionality scaling for the random walk MCMC, but not the Mala. I think it's mostly a technical problem, not really. I mean, it should be feasible. Questions that are involved are parallelism, also like distribution of data, that kind of stuff. Being able to use stochastic gradient information when the dimension is really, really big. You don't want to use all your informations at each time step. And use intractable models, so models where you can't evaluate those densities. Right? These are the things I have on my list. And with that said, I'll stop here. I think I'm 100.
Thank you. Yeah, we have gone over the hours, so maybe we'll move upstairs. And you're all welcome to join us. It's pretty biscuit and very thank you. Neck and tired.
It is calibrated for 15 minutes.
Yeah, well, I realised that, yeah. You're finely tuned.
Yeah.